Well, hello 3C. We're going to talk about exponential growth today and applications of exponential growth. And our goal, I can create equations for exponential growth situations. So here we go. We're going to talk about exponential growth. Now, we've already actually looked at one of these problems in class. This is sort of a rough idea of the problem that we've actually looked at. Say we start with 5 cents and each day thereafter receive an additional amount equal to our total from the day before. How much money do we have on the 10th day, the 20th day, or the 100th day? So we don't actually want to calculate every single amount right up to the 100th day to be able to calculate that. So we got to figure out some sort of a pattern here. So on the first day we have 5 cents. On the second day we get an additional 5 cents to make it 10 cents. On the third day, we're going to get an additional 10 cents because we get the same amount as we had the day before. So on day 3, we now have 20 cents. And on day 4, we're going to get an additional 20 cents to have 40 cents. So if you take a look at what we've actually done here, what I've done is I've taken the amount from the day before, which was 0.05 cents, and I've just times it by 2 because I got the additional amount on that. And here I took the amount I had the day before. Now I'm going to use this version of it, 0.05 times 2. That's the amount we had. And then I times it by 2 again to get that 20 cents. Whoops. Whoa. I hate it when it does that. There we go. So now we have another 2. And then if I do it one more time here, 0.05, 2 and 2, that's the amount I had on the day before. So this is equal to the 20 cents I had the day before, and now I'm going to double it to get to that 40 cents. So I give it another 2. So if you take a look at what we've actually got here, this is our beginning amount, 0.05, times 2 to the exponent 1. This is 0.05 times 2 to the exponent 2, and this is 0.05 times 2 to the exponent 3. So in this particular situation, and you're going, well, what about this 0.05? Does it follow the pattern? Yep, it most definitely does. It's 0.05 times 2 to the exponent 0, because 2 to the exponent 0, as we took before, is actually just 1. So then I just have 0.05. Now I could keep going with that pattern until I get to the nth day. And on the nth day, I have 0.05 and then times 2. Well, to what exponent? Let's take a look at all of these ones. On day 1, I had 0. On day 2, I had 1. On day 3, I had 2. On day 4, I had 3, and so on. It looks like I have 1 less than the day of the month that we started on. So, n is our day, and I have to take 1 away. So here's our equation. And I'm just going to point to a few things on here. The first thing is that this was our start amount. Starting amount. And this 2, this is our doubling factor, how much we're increasing our money by. And then this n minus 1 is how long it's been doubling. How many doubles? Now, a lot of situations don't actually take the 0 case as day 1. They say that that's your beginning point and then it works from there. And what we have is this general equation where we have our y is being the current value of what we're looking at. So that is the total of this whole thing. Our a is our starting value. Our b is called our growth factor, and our x is called the number of time periods. So the number, how many doubles up here, how many time periods it happened in. So looking at the next one here, when the growth factor is given as a percent, b equals 100%, so it's growing, so you retain 100% of the value that you had prior to that, plus a little bit more. And so the way we actually do that, we take 1 as our 100 and then add our percent as a decimal. So in the case of the example of 5%. If I want a growth of 5%, first of all, I have to write 5% as 0.05. And then B actually equals 1, which we talked about stands for 100%, plus 0.05. So our growth factor is 1.05. So let's take a look at this situation. Chris buys a rare car in 2014 that increases in value by 2% every year. This is actually a rare car indeed. Very few cars would increase in value, but let's say that this is some sort of an antique car and he takes very good care of it, and it's going to grow in value by 2% every year. So we're going to create a situation, an equation for this situation. Now we need the general form, and I will always give you this general form, and you'll have to fill in some information to make it specific to each question that you're looking at. So y equals a b to the exponent x is our general form. And I'm just going to switch colors up here a little bit. And what is this in this situation? Well, we're trying to talk about the value of the car. It increases in value. So I'm going to use a V instead of the Y. V standing for value. Now A, we were told, is our starting amount, and I didn't actually give you a starting amount here. I should have. I'm going to fill that in. Chris buys a rare car in 2014 for $25,000. Okay, so we'll put that little bit in there, which means that $25,000 is actually our starting amount. So I'm going to put $25,000 in here. Our B factor, well, this car retains 100% of its value, and then we have to add in what it increases by. So it increases by that 2% every year. We've got to write 2% as a decimal. It's not just 2, it's 0.02. And this X, let's call it N for number of years. Okay, so here's our situation, and I'm going to simplify that a little bit. That's going to be 25,000, and our growth rate is 1.02 to the N, where N stands for the number of years since 2014. So maybe I should just put that in there. N is the number of years since 2014. Okay, so how much will the car be worth in 2040? Well, in 2040, we have to figure out what we're being asked to find. So up in my equation here, I have V equals 25,000, 1.02 to the N. So how much will the car be worth? I'm looking for its value. So I'm trying to find V, which means if I'm looking for V, I must fill in something for N. Well, in 2040, how long has the car been increasing in value? From 2014 to 2040 is 26 years. Okay. So our N is going to equal 26 years because it's been increasing in value for 26 years. Okay. So let's just plug that in. 25,000, 1.02 to the 26. And I'm going to pull up my handy dandy little calculator here, and I'm going to show you how to punch this in. So you're looking for a button that looks something like this one here, y to the x. It might be x to the y. It could be a little, here, I'll just draw them out here. It could be y to the x, or x to the y, or it could be a little hat, an up arrow, looking like that, or in some of the newer calculators you'll see it has an X with a little box beside it. So any one of those could actually mean your exponent button. So in this case, it's this one here, this y to the x. And what I'm going to do, and this works on all calculators, I'm going to punch this part of it in first. So I'm going to highlight this part here. This is what I'm going to punch in first. 1.02 to the exponent 26, and I'm going to hit equals. Now, I'm not going to write that down. I'm just going to leave it on the calculator and multiply that, because this means multiply in between there. I'm going to multiply that by 25,000. So just go times 25,000 equals. So the car is worth $41,835. see if I can remember that. $41,835. And how many cents? 45 cents. So there's how much the car is going to be worth. Let's go on down here. When the growth factor is given as a factor or just a number. So if you're given a number, you use that number for B. And what I mean by a number is if it uses words like these words here that I'm going to highlight. Something doubles, or something triples, or something increases by a factor of 5. So what's our B going to be? Well, if B doubles, B means that we're multiplying by 2. Remember, B is what we multiply every time. If it doubles every year, we have to multiply it by 2. Triples, I hope you know, multiplies by 3. And if you ever see the word increases by a factor of something, it's actually giving you what we're multiplying by. B equals 5. So let's take a look at the next wrong button. There we go. The number of text messages David gets in math class triples, there's our word, triples every day. Write an equation that models this situation. Okay, we need our handy dandy little general form. Y equals AB to the X. Now here we're talking about number of text messages, the number of text messages. So I'm going to call that a capital T. And it triples every day. Well, we don't know what it started at, so we're going to assume that it actually started at 1. So I'm going to put in a 1 for my A value. And since it triples, our B is 3. And it triples every day. So I'm going to put a D up here where the X is as a stand-in for numbers of days. Okay. And I get a she. It says if he starts with 2, let's call that texts. In math class, write a new formula. Well, what's going to change here if he starts with 2? Well, it's this initial value that I said before. We weren't given an initial value, so we're going to assume it was 1. Now I'm given the initial value. So this is going to be T equals 2, still triples every day, so 3 to the exponent D. Now, how many messages will he have after 5 days? So what am I given here? Let's get my highlighter. I'm given 5 days. So that days has to go into the D up there. So we have number of text messages T equals 2, 3 to the exponent 5. Well, let's punch that into my handy dandy calculator. I'm going to go 3 to the exponent, looks like that, 5, and I'm going to hit equals. And that's 243. And now I just have to times it by that initial amount. So now I'm going to times it by 2 equals 486. So after 5 days, you get 486 messages in math class. That's a lot of messages. Next question. Yep. If this pattern continues, how many messages will he get in math class the last day of the semester if there are 90 classes in the semester? So if this pattern continues, well, what are we going to do with that 90? Well, on day 90, that means that our exponent, which was days, is going to be 90. Now, if that was 486 after 5 days, 90 days is going to be astronomically huge. Let's have a look at this. I'm going to punch this in again. Remember, the part I punch in first is this 3 to the exponent 90. We're going to punch that in. 3 to the exponent 90 equals. That is a really big number. Look at that. This e to the 42 means that this thing has to move forward 42 spaces to actually give me the number. I'm going to write it down, but first I'm going to multiply that by 2 times 2 equals, and now I'm going to write that down, 1.75 times 10 to the 43. 1.75 times 10 to the 43. Now, what does this times 10 to the 43 mean? You may have seen that in science class. It's called scientific notation. And what it means is your calculator is saying, this number is too big. I don't have that many spaces. So what I'm telling you is it's this number, but you have to times it by 10 43 times. Now, timesing by 10, all it does is move the decimal place over. So if I times this by 10 43 times, I have to move this over 43 times. Now, I'm not going to write that out because it's just going to be 1, not my highlighter. It'll be 175, and that moves it over 2 spaces, and then I would have to write 41 zeros after this. 1, 2, 3, 4. I'm not doing it. Nope, not going to do it. I'm going to leave it in scientific notation. That's the whole point of scientific notation. This number is too big to write across my page. 1.75 times 10 to the 43. That is huge. And that actually puts us at the end of this exponential growth video.